Today we are going to prove the rank nullity theorem. According to this theorem, if V and W are the two vector spaces over same field F and T is any linear transformation mapping from V to W. If V is a finite dimensional vector space, finite dimensional means the basis of V will contain finite number of elements. Then prove that rank of T plus nullity of T will give dimension of V. For understanding the topic of rank nullity theorem, it is very important to know the terms like what is rank, what is nullity, what is null space, what is basis, what is dimension, etc. So, here we will start from what is null space. If V and W are the two vector spaces over same field F and T is any linear transformation mapping from V to W, then null space of T will be denoted by NT and it will contain those element of V, it will contain those element of T whose mapping will give 0 vector. That means here given V and W be the two vector spaces, remember, over same field F and here LT. Here the mapping is linear transformation mapping from V to W. So null space of T will contain those elements of V whose linear transformation mapping image will give 0 vector of this vector space. I hope it is clear that what is null space of T? It contains those elements of vector space V whose linear transformation mapping will give 0 vector of W, or we can say identity element of W vector space. So now we can define the term nullity. Nullity of T. It is the dimension of null space of T. It means this set. Okay. So what is nullity of T? It is the dimension of null space of T. What is dimension of any vector space? It is also vector space. Remember, it is also vector space. We can prove it by theorem. So now, what is dimension of any vector space? Dimension of any vector space means number of elements present in its basis. It means here the number of elements present in basis of this null space of T will be the nullity of T. Here it is written nullity of T is equals to dimension of null space of T. It means number of elements containing the basis of null space of T. Now what is range space? If V and W are the two vector spaces over same field F and T is the linear transformation mapping from V to W, then range space of T will be a set which is defined by it contains those elements of W, it contains those elements of W which are the images of the elements of V. See from here, if V and W are the two vector spaces over same field F and LT is the mapping, then range space of T denoted by this symbol will contain those elements of W which are the images of elements of V. Here V is a vector space and W is a vector space. Both are on same field F. LT is the mapping defined here. So range space of T will contain those elements of W which are the images of elements present here. So if alpha belongs to V, then its image will be given by T of alpha. So we can say T of alpha, or we can say beta is the element of W. It means this set range space of T will contain those elements of W which are the images of elements of V. Same as the case of nullity, here rank of T may be defined. It is the dimension of range space of T. Dimension of range space of T means number of elements present in basis of range space of T will be the rank of T. So now it is clear that what is rank of T, what is nullity of T. Also we are aware about what is dimension of any vector space. It is the number of elements containing its basis. So now what is basis? Here if V is a vector space over same field F. Remember, the elements of V will be vectors, but the elements of field F will be scalar. Now, if V is a vector space over same field F, then any subset of V or linearly independent subset of V. Here, if V is a vector space over same field F and B will be the linearly independent subset of V which also spanned V. It means any subset of V which is linearly independent subset, and second it is spanning vector space V, then B will be the basis of V. That Li subset of V which is also spanning it is known as basis of that vector space. Spanning V, it means that every element belonging to V can be written in linear combination of the elements of this basis. Here alpha 1, alpha 2, alpha 3 dash dash alpha n are the elements of this basis. Let me repeat this again. If V is a vector space, then that linearly independent subset of V which is also spanning it will be the basis of that vector space, and every element belonging to V can be written in linear combination of the elements of its basis. So our theorem here is rank nullity theorem. Its statement is as given. Now we have to prove that rank of T plus nullity of T will give dimension of V. So if here given T is the linear transformation mapping from V to W, V is a finite dimensional vector space, okay. Here null space of T is also a subspace of V which is also finite. So it can be proved by theorem, okay. Then letting that dimension of V is n and dimension of nt is m. It means basis of vector space V will contain n elements and basis of nt will contain m elements. Now putting these values here, we have to prove that rank of T is n minus m. Now since dimension of null space of T is m, we let here, so let B1 having m elements be the basis of this null space of T. So B1 is basis of null space of T. I have already told that basis of any vector space or subspace is the Li subset of it. So B1 is basis of null space of T, which is also a vector space, or we can say subspace of V. So B1 is Li subset of V. Okay, because B1 is basis of null space of T. B1 is Li subset of NT, and NT is subset of V. It is by definition of subspace. Okay, subspace of any vector space is the subset of V, which is also a vector space over same field F. Now, NT is subset of V, B1 is subset of NT. So automatically B1 will be the subset of vector space V. Here written B1 is also Li subset of V, because B1 is Li subset of NT. So it can be written that B1 is a part of basis of vector space V. Let basis of vector space V is B2. Now B2 will contain n elements, because here we let that dimension of V is n. So B2 will contain n elements. Here B1 is a part of basis of V. So this is the basis of NT. It is the part of basis of V. Now since B2 is basis of V, so by definition of basis, B2 will be the subset of V. It means all the elements of B2 will be belonging to vector space V, because B2 is subset of V. Now if these are the elements of V, so we can define their mapping such that T of alpha 1, T of alpha 2 to T of alpha n, these all will belong to the range space of T. Remember here I have told that range space of T will contain the mapping of elements of V into W. So beta, or we can say that beta is equals to T of alpha. So this element belongs to W, or range space of T. T of alpha will also belong to range space of T. Here T of alpha 1, T of alpha 2, etc. to T of alpha n will be belonging to range space of T. Let us consider a set from here, which is T of alpha n plus 1 to T of alpha n. Here these are n elements. Here B2 is basis of V. We let that dimension of V is n. It means number of elements in basis of V will have n elements. Here n elements will belong to V, because B2 is Li subset of this vector space. Now we have defined their mapping, so these are also n in numbers. Now these are m elements, these all are n elements, so a set remaining here will be n minus m elements. So we will consider a set B which contains n minus m elements. Now if we are able to prove that this considered set is the basis of range space of T, we will prove the theorem that rank of T will be n minus m. Here rank of T means dimension of range space. Dimension of range space of T will be n minus m, and dimension of range space of T means number of elements in basis of RT. Our aim is to prove that basis of RT will contain n minus m elements. Here we have considered that a set B is containing n minus m elements. So if we can prove that this B is basis of RT, our theorem is proved. Now B is the considered set having these elements is basis of RT. We have to show that. Now for proving any subset of any vector space B to be its basis, we have to prove 2 points. First, that it is an Li subset, and second, that it is spanning that vector space. So we will firstly prove here that B spanned RT. that is B is spanning range space of T. Now, letting an element from range space of T will be beta. We know that beta is equals to T of alpha. Now, we know that alpha belongs to V. There exist some scalars belonging to field F. Now, alpha is belonging to V. Alpha is an element of vector space of V. So, and alpha 1, alpha 2, alpha m, say alpha n. And B2. B2 is basis of V, which is containing n elements. So, alpha is an element of vector space V. B2 is basis of V. So, alpha can be written in linear combination of elements of its basis. So, alpha can be written like this. Now, beta is equals to T of alpha from here. So, putting the value of alpha from this equation, we are getting this. Now, T of C1 alpha 1 plus C2 alpha 2 dash dash Cn alpha n. We can write this statement like this by the property of linear transformation. It is by property of linear transformation. Okay. Now, we know that alpha 1, alpha 2, alpha m, these are the elements of B1, which is basis of null space of T. B1 containing alpha 1, alpha 2 to alpha m. Now, B1 is basis of null space of T. It is also a Li subset of NT. That means these elements also belong to NT. These elements are belonging to null space of T. And I told you that null space of T will contain those elements of vector space of V whose image is 0 vector. That means the image of these elements will be 0 vector. Hence, T of alpha 1 will be 0, T of alpha 2 will be 0, T of alpha m will be 0, because alpha 1, alpha 2, alpha m are belonging to B1 and hence belong to NT. So, the remaining part will be beta is equals to Cm plus 1 T of alpha m plus 1 to Cn T of alpha n. Now, see, here the considered set B is containing these elements. Now, an element, any general element belonging to range space of T, that is beta, is written in linear combination of elements of this considered set. It means this set is spanning RT. This set B is spanning RT because any general element of RT can be written in linear combination of the elements of B considered set. Okay, so the first part of theorem is proved. Now we have to prove the second part, that B is Li subset of RT. For proving any subset with a linearly independent subset, we have firstly to put this equation is equals to 0, or we are simply putting beta is equals to 0. Now, these are the scalars belonging to F. Now, this linear combination is equals to 0. Then we have to show that Cm plus 1, Cm plus 2 to Cn all will be equal to 0. Only then this set B will be the Li subset of RT. Here we have to see that what is Li and what is LD. Linearly independent and linearly dependent. For proving any subset being linearly independent, firstly we have to write them in linear combination and putting them equal to 0. Now we have to show that C1 is equals to C2 is equals to C3 all will be 0. It means all these scalars will be 0. Here we have to show that B2 is Li subset. It means the elements of B, that is these elements, we will first write these elements in linear combination and then putting equals to 0. Now we have to show that these scalars, all these scalars are 0. By definition of linear space, this statement can be written like this. Now here we see that T of an element is equals to 0. Image of any element is giving 0 vector. It means this element will belong to null space of T. Because null space of T is containing those elements of V whose image is 0. Here image of this element is 0. So this element will belong to null space of T. Let there exist A1, A2, A3, Am be the scalars of field F. Now Cm plus 1, alpha m plus 1, this element is belonging to null space of T. This element is belonging to null space of T. We know from here, we know that B1 is equals to this is basis of NT. It means that every element belonging to null space of T can be written in linear combination of these elements. Here, this element is belonging to null space of T. It means that this element can be written in linear combination of the elements of B1. Here, alpha 1, alpha 2, alpha 3, alpha m are the elements of B1 or the basis of null space of T. So this element can be written in linear combination of these elements of B1. Here scalars are given like this. Now transforming these values from RHS to LHS, we are getting this equals to 0. We know alpha 1, alpha 2 to alpha n. Alpha 1, alpha 2 to alpha n. These all are the elements of B2, which is basis of vector space V. These are Li, and these are Li. It means that their scalars will be equal to 0 by definition of linearly independent subset. Okay, so all these coefficients, or we can say all these scalars belonging to field F will be equals to 0. All these are equaling to 0. So these scalars will also be equal to 0. That means Cm plus 1, Cm plus 2 to Cn all will be 0. Here we have put that linear combination of these elements equal to 0, and we are getting that these scalars are 0. So we can say that these are Li by definition of Li. So from first part we have proved that B is spanning RT. From here we are proving that B is linearly independent. So it is proved that B is basis of RT. Now the considered set B is basis of range space of T. It means that number of elements of B will be the dimension of range space of T, and dimension of range of space of T will be the rank of T. So simply we can say that rank of T is the number of elements in B. The number of elements in B are n minus m. So rank of T will be dimension of V minus nullity of T from here. Hence our theorem is proved that rank of T plus nullity of T will give dimension of V.